Hi, this is Thomas. Welcome to math class. Our topic is differential calculus. We're looking at related rates. We're going to see how to use differential equations to calculate the rate of change in a variable over time based on the rate of change of a related variable over time. So let's look at an example. A triangular trough with dimensions 10 feet long by 2.5 feet high by 2 feet wide is being filled with water at a rate of 5 cubic feet per minute. What is the rate of change in the height of the water when the water is at a level of 1 foot 3 inches? In working with related rates problems, the first step is to create a diagram. Sometimes a diagram is given. In this case, we want to create one. I have a triangular trough. So I'll draw the end as a triangle shape. The length of the trough is 10 feet. The height of the trough is 2.5 feet. And the width of the trough is 2 feet. I have some additional information about measurements relating to the trough, but these measurements are changing. And so I'm going to use variables for the height of the water currently, h, and later I'm going to see that I'm also going to need a variable for the width, let's say, of the water. I'm going to call this B for base. It's the base of the smaller triangle that's formed by the height of the water at the current point. Now that I have my diagram, step 2 is rates. I'm given a rate, and I want to identify the rate that I'm asked to calculate. The rate I'm given is the change in volume over the change in time, which is 5 cubic feet of volume per 1 minute. And the rate I'm asked to calculate is the change in height over a change in time. So this is what I'm solving for. Now I've identified my rates. Step 3 is a formula. And I want a formula with one variable. So to start, I'll determine the formula for volume. Volume of a triangular prism is 1/2 times base times height times length. Now the volume I'm calculating, that I'm working with, isn't the volume of the trough. It's the volume of the water at its current level. And that level is changing, thus I'm using a derivative. So I'll start by calculating or creating my equation given the fixed measurements, 1/2 times base times height times 10. The length of 10 is unchanging, but the base of the water is changing and the height of the water is changing. In particular, it's the height that I'm focused on. And I have two variables right now, base and height. What I need to do is I need to substitute in a value for B in terms of h so that I'm only working with one variable. Now if I look at the triangle face of the trough, I can see that the base to height relationship is 2 over 2.5. And I can use cross multiplication. 2h equals 2.5 base, and divide both sides by 2.5. And now I have the value 0.8h equals base. And I can substitute this into the equation. Volume equals 1/2 times base becomes times 0.8 height times height times 10. So notice that I've substituted in for b the equivalent value of 0.8h, and now I have an equation with one variable. And I can simplify to volume equals 1/2 times 0.8 times 10 is 4h squared. Step 4 is differentiate. Now I'm going to expand that description in just a moment, but let's look at how we would differentiate typically this function. I would take the derivative of volume relating to change in height as 8h. But in this case, I'm not looking to differentiate in terms of height. I'm looking to differentiate with respect to time. So the differentiation with respect to time is going to be the differentiation with respect to height, 8h, times the differentiation of height with respect to time. This is the related rate concept that we're implementing in this equation. Now we can go to the final step. Step 5, substitute and solve. What I have in step 4 is 3 variables. The differential of volume with respect to time, height, and the differential of height with respect to time. And I know 2 of those values. The differential or change in volume with respect to time is 5. That was a given in the original problem. Equals 8 times height. The current height is 1.25. That's where the water is right now. The 1.25 is coming from the given of 1 feet 3 inches, which equals, in decimal form, 1.25 feet. And I'm using that value as my input for h because the problem is asking me to evaluate the rate of change at the point at which, or at the time at which, the height of the water is 1 feet 3 inches, or 1.25 feet. And my final variable, which is what I'm solving for, is the derivative of height with respect to time, the change in height in relation to the change in time. And I can solve by dividing both sides by 10, which is 8 times 1.25, to get to a value of 1/2. And that is the answer. The change in height with respect to change in time is 1/2 foot per minute. Now to conclude, I'm going to make some comments on each of these 5 steps to give you guidance. Number 1, with the diagram, make sure that in the diagram the numbers are fixed, unchanging values, and for any values that are changing, use variables. So in our case, the height given in the problem of 1 feet 3 inches, I've used the variable h because that's something that is changing. I don't want to use 1.25 until I go to step 5. So in the diagram, be sure to use values only for unchanging measurements, and for measurements that will change, use variables. Step 2, rates. You'll be given one rate, and you need to identify the rate that you're solving for. That's what the question is asking for. both of these rates are set to change in time. We're not looking at how they change to each other directly. We want to know how one changes with change in time, and then we'll work through the analysis to determine how the other changes with respect to time. In the formula, make sure that you end up with a formula that only has one variable. In our example, we had two variables, base and height. If you have this situation, go back, look for a relationship between the two variables, use equivalency and substitution to get to an equation that only has one variable. 4. When you differentiate, make sure you differentiate not one variable with respect to another, but each variable with respect to time. And again, in step 2, we saw we were given one of those rates, and we're asked to calculate the other rate. And that's what we do in step 5. We substitute in values. The one value that will be missing is whatever we're asked to solve. Usually that's going to be a change in a particular measurement with respect to a change in time. Related rate contexts can vary significantly from one problem to another, and these problems do require significant practice. If you use this 5-step procedure, you'll be able to solve these problems successfully. This ends the lecture on differential calculus related rates. Thanks for watching, and I'll see you in the next lesson.